Let's imagine we've got a motion that looks like this. It's got this functional dependence. X is equal to 3 meters per second squared, t squared. And let's see if we can figure out what's the velocity of this thing as it's moving. This tells us the position as a function of time. Let's see if we can figure out what's the velocity as a function of time. Let's pick some initial time, t1, some arbitrary value for the initial time, t1. Well, we know then that x1 will equal 3 meters per second squared, t1 squared. And then at some later time, final time t2, our position will be x2 will be 3 meters per second, t2 squared. Now let's imagine that our t2 is some time delta t later than t1. We know that delta t is t2 minus t1, so that t2 will be t1 plus delta t. So let's put in t1 plus delta t for t2. So here all I have done is substitute t2 with t1 plus delta t. Now let's square this. What do we get? We get 3 meters per second squared. And then this squared is t1 squared plus 2 t1 delta t plus delta t squared. And multiplying that out, we get 3 meters per second squared t1 squared plus 6 meters per second squared t1 delta t and plus 3 meters per second squared delta t squared. There we go. Now, we want the displacement, which is, remember the instantaneous velocity is the limit as delta t goes to 0 of delta x over delta t. So we want the displacement delta x, which is x2 minus x1. So we're going to take this term, which is x2, and subtract x1. But notice this first term, 3 meters squared t1 squared, that's the same. So this minus that, this cancels, and all we'll have left are these two terms. The 6 meters per second squared, t1 delta t, plus 3 meters per second squared, delta t squared. To find the average velocity, we then have to take delta x and divide by delta t. So let's take this and divide by delta t over delta t. And what happens? When we divide off a delta t, this term cancels off. And we've got delta t squared. One of those will cancel off. There we go. So we now want to take the limit as this thing has delta t go to 0. So what do we have? The limit as delta t goes to 0, we'll put in here the limit as delta t goes to 0. Well, what do we have here? We've got 6 meters per second squared t1. This term doesn't depend on delta t. So as delta t goes to 0, that term's not going to do anything. All it depends on is t1. Whereas here, we've got 3 meters per second squared times delta t. As delta t goes to 0, this product is going to go to 0. So all we have left is this here, and that then must be equal to the instantaneous velocity. Now, notice we used some arbitrary initial time t1, so this would be the velocity, the instantaneous velocity at time t1, or if we just want to say any arbitrary time t, we could say that the velocity as a function of time is equal to 6 meters per second squared times t. But if we know how to take derivatives, what's the derivative? What is dx dt right here? Well, how do we take a derivative with a term with a power? We know we multiply by the power, which gives us 6 meters per second squared. We subtract 1 from the power, with leaving us with t, and that's exactly what we found. So going through this definition of our initial velocity, it certainly does seem to indicate that this is exactly equal to the first derivative with respect to time, dx dt. Okay, very, very good. So what we found is if the position as a function of time can be written as 3 meters per second squared times t squared, then what we find is the velocity, the instantaneous velocity as a function of time, is 6 meters per second squared times t. Now let's just notice one more time what the units are. If the units of t are in seconds, we'll get second squared cancel, we get position in terms of meters. And which is correct, that's what we want, position in terms of meters. Here, if t is in seconds, one of the seconds cancel, and we'll end up with the units of velocity are meters per second, and that works out also. That's exactly what we would hope, so that's good. What do we notice about this motion? First of all, we notice that the velocity is not constant. As time increases, the velocity increases. We might make a little table just like we did before with t and velocity now, and I'm just going to emphasize t is in seconds and the velocity is in meters per second. When t is 0, 0 here, velocity is 0. When t is 1, the velocity is 6. When t is 2, the velocity is 12. When t is 3, 3 times 6, the velocity is 18 meters per second. What we notice is that as time increases, the velocity increases. So what would this motion look like? Well, this is something that's speeding up. It's going faster and faster and faster. If you're driving on the highway, you don't always maintain the same speed or the same velocity. You might, as you get on the on-ramp, you might speed up so that your velocity is increasing. If you're going to pull off the off-ramp, you might slow down. In that case, your velocity would decrease. So your velocity is not always constant. It changes. So just like we did before, we can talk about the change in the velocity. When the velocity changes, the rate of change of the velocity is what we call the acceleration. So let's take a look at that. We will define acceleration as the rate of change of velocity. So we're going to define this in a very similar way as we defined first average velocity and then instantaneous velocity. We'll define average acceleration and then instantaneous acceleration. So we'll define the average acceleration as delta v over delta t. Remember, the average velocity was delta x over delta t. Average acceleration is delta v over delta t. And the instantaneous acceleration will then be the limit of the average acceleration as we look at a smaller and smaller time interval. In other words, as delta t goes to 0. In other words, the instantaneous acceleration is equal to the limit as delta t goes to 0 of delta v over delta t, which, as we've seen, is just the derivative of the velocity with respect to time, dv dt. As the delta t goes to 0, the delta terms go to 0, I should say they become infinitesimals. So delta v goes to dv, delta t goes to dt. But we know that that's just the derivative of the velocity, and the velocity is the derivative of the position, so dx dt. So the instantaneous acceleration is going to be the second derivative of the position with respect to time, d squared x dt squared. All right, well, that is very interesting. Let's take what we derived before, put it in here. Let's take this limit and see if we can figure out what is the acceleration as a function of time. Okay, here we go. Let's pick some initial time t1 with a velocity v1 so that we have v1 is equal to 6 meters per second squared t1. That's our initial time and corresponding initial velocity. And then a final velocity at a final time t2 so that we have v2 is equal to 6 meters per second squared t2, our final time. And t2 we'll define as our initial time plus the time interval delta t. So with t2 equal to t1 plus delta t, we've got v2 is 6 meters per second squared times t1 plus delta t. Multiplying this out, we have 6 meters per second squared t1 plus 6 meters per second squared delta t. Now let's find that change in velocity delta v, which is v2 minus v1. So this term, v2 minus v1, notice this first term cancels out. So these cancel out, and all we're left with is 6 meters per second squared delta t. That's going to be delta v. Now we'll take that, divide by delta t, and we notice the delta t cancels. So all we're left with is 6 meters per second squared. We take the limit that delta t goes to 0, But there is no delta t, so it doesn't matter. That's just a constant value. As delta t goes to 0, that does not change. And this is going to be our instantaneous acceleration. So what do we find? Our acceleration is 6 meters per second squared. In this case, it's a constant value. It does not change with t. It is independent of time. It's just constant. So what we have is a uniform acceleration. Uniform acceleration just means a constant acceleration. A constant acceleration of 6 meters per second squared, which gives us a velocity that's increasing with time, 6 meters per second squared times t, which then gives us a position which is increasing with time, but it's increasing as t squared as opposed to linearly with t. All right, very, very interesting. Let's go along with this a little bit more. So what have we done? We start out by describing the position of an object with some functional form, x as a function of time. And this could have any functional form that we want for the time being. The velocity, we then found, was the first derivative of the position as a function of time. In other words, v is equal to dx dt. That's the instantaneous velocity, which we'll just refer to as the velocity from now on. The acceleration is what we found in general, a function of time, is then the first derivative of the velocity with respect to time. So dv dt, but with v equal to dx dt, a is then d squared x dt squared, the second derivative of the position with respect to time. Okay, very good. Now there are some restrictions as to what can actually be physical motions. There are some functions that you could define that actually would not correspond to physical motions, but we'll talk more about those later. But for now, we can basically assume that we'll use anything we want. All right, very, very good. What about, we've got a x, we've got dx dt, d squared x dt. What about higher order derivatives? Do they represent physical quantities? Well, yes, the fact of the matter is they do. However, they come up much, much less often than these, and consequently, they don't have uniformly defined names, so to speak. There is the first derivative of the acceleration, dA dt, which would be the second order derivative of the velocity, or the third order derivative of time. This is sometimes called the jerk. So we've got position, velocity, acceleration, and jerk. Sometimes it's also referred to as the jolt. Often just the symbol used for it is J. Now if we think about that, if you are accelerating down the highway, say, the car is accelerating in a uniform pace, you kind of can feel that as a uniform motion. But imagine that you change that acceleration very abruptly. Maybe the easiest thing to do is imagine someone is pulling you with a rope and they're constantly pulling you at a constant rate, but all of a sudden they pull on it very abruptly. They jerk on the rope. That's a change in the acceleration, and that's where the idea comes from. A jerk is a change in the acceleration, so rather than a constant pulling force acceleration, it's a sudden change in that, which you might describe that as a jerk or a jolt. Well, what about the higher order derivatives? These have even less uniformly accepted names, but there are some that are used sometimes. d4x dt4, d5x dt5, and d6x dt6. The fourth derivative is sometimes referred to as the snap. The fifth derivative is crackle. And the sixth derivative is pop. Snap, crackle, and pop. Perhaps you've heard of those somewhere else. Okay, but like I said, those are not uniformly accepted in the scientific literature, you might say, but they are certainly physical quantities that you could calculate if you wanted to. All right, very, very good. Let's see about, one more thing, let me just mention. Because it does come up so often, let me just mention one specific case. if you have a position as a function of time with this kind of polynomial form, so we've got some constant times, let's say, t to some power n, then just remember that the first derivative of that, to make the first derivative, we bring down this factor of n, so this is n times c times t, and then we subtract 1 from the power. So that's something that kind of pops up often, so it's a good thing just to keep in mind, to differentiate a monomial term with just a power like this, t to the n, bring down the factor of n times the initial constant, and then subtract the power by 1. Okay, very good. What we're going to do now is we're going to start looking at a very specific kind of motion, and that is one with a uniform acceleration. Now that's something we came up with here, but we're going to look at a more general kind of acceleration, a general kind of motion with any uniform accelerated motion. That is uniformly accelerated motion. Let's take a look at that.